the following statement true, that if you take the intersection between A and B and take the union of that with A, you just get A back? Well, let's think about it logically, right? The left-hand side simply is saying that if you take two sets, A and B, you take their intersection, which is going to be this section right here, that's what that is, and then you take the union of that with A, so if this was our A and this was our B, union with A would just be everything in A. Now at the end of the day, you're just going to be ending up with A, and that looks to be true, right? Everything we've highlighted is just the set A. What if A and B don't share anything, right? What if they're two separate? There is no intersection. Then A intersect B, there's nothing for you to shade in, but you still can unionize. I'm going to call that unionizing. I don't even know if that's the correct word, but I'm just going to say that unioned with A is still just going to have you highlight A because you want everything in A. So you still get A back. So this looks like it's going to be true. So let's go ahead and prove that. So we have to recognize this is going to be an equivalence, which means we need to prove that A union with A intersection B is a subset of A, and we have to show that A is going to be a subset of A union A intersection B. We have to show everything on the left is on the right and everything on the right is on the left to say that they are the same. So let's begin our proof. So to start our proof, notice it's a for all proof. There are no restrictions on what A and B are. So we need to clarify that this is for any A and B, which means it's a for all, which means we start with a let. We say let A and B be sets. Fantastic. Now we can start getting into our first case, proving the left-hand side is a subset of the right-hand side. So how are we going to prove that this is true? Well, first we're going to say that we're going to start with the left-hand side, right? We're going to start with A union with A intersect B. We're going to start here, and our goal is going to be to get to A. Now, how are we going to show that this is a subset of that? Well, we need to show that every element here is going to be here, which means that we can create a representative element X. This X is going to represent any element in this set. And if we can just show that X can also be in here, then we've shown that every element here can be in here. Fantastic. So let's do that. First, let's start by breaking up what it means for X to be in this beginning set. Well, for X to be in A union bracket A intersect B close bracket, it means that X is an element of A, or X is an element of A and X is an element of B. Fantastic. Okay. So where can we go from here? Well, obviously, if X is an element of A, you can go here. The or, this is the part I'm struggling with. Could you just say that if X is an A, then you could just say that maybe you could just immediately go there, I'm thinking, right? Yeah, that seems to make sense to me. If X has to be an A, then obviously X is an A. Yeah, I think that should suffice in our logic. So let's quickly write down this part of the proof. So we start by supposing our representative element X. So we say, suppose X is an element of A union open bracket A intersection B close bracket. Then we want to break apart what that means. This means then X is an element of A and X is an element of B, or X is an element of A. Yeah, I don't even know if you need to write down this second part, but I'm just going to do it just in case. And now we can just say, okay, since X is an element of A in both cases, then X is an element of A. Inherently making A union with A intersect B a subset of A. Fantastic. Okay. Yeah, in both cases, X is going to be an element of A. Great. Okay. Now we can move on to our second case. Okay, while writing out the second case, I already realized that this is going to be super simple. So of course we want to show that any element in A is any element Y, for example, is also going to be an element in A union with A intersect with B. So obviously, since it's an A, it's obviously going to be in here, right? This is a direct link that for it to be in here, it has to be either in here or in here, and it's already in here, so we can just immediately say that y is obviously going to be in here. So let's go ahead and write this down. So we can say, suppose y is an element in A, then y is going to be an element in A unioned with A intersect with B by definition of union. Fantastic. So, or we can say then, continue the sentence and say making A subset of A unioned with A intersect with B. Great, and now we just write our concluding statement now that we've shown the case, both the first case and the second case are both going to be true. So we can say in conclusion, since A union open bracket A intersect with B is a subset of A, and A is a subset of A union A intersect with B close bracket, then A union open bracket intersect with B close bracket is equal to A. So we've shown that this statement is going to be true.